In this section, we'll talk about one application of double integrals, which is the probability. Suppose that we have one variable function, f, which denotes the probability density function of a continuous random variable x capital. Then the probability, which is denoted by p, that the random variable x capital lies between two values a and b, will be given by the integral from a up to b of f of x times dx. Now, in two variables, we consider two random variables, x capital and y capital. Then the joint density function f of x comma y of the two random variables x capital and y capital is a function such that the probability that the set x capital y capital lies on the region D is given by the double integral over the region D of f of x comma y times dA. In the special case where the region D is a rectangle, then the probability that x capital lies between the values a and b and y capital lies between the values c and d will be given by the integral from a up to b and the integral from c up to d of f of x comma y times dy dx. Now let us see an example. Suppose that we have two students that both have classes that end at noon and they agree to meet every day after class. They arrive at Starbucks independently, and student X's arrival time is X capital and student's Y arrival time is a Y capital, where X capital and Y capital are measured in minutes after noon. The individual density functions are f1 of x is equal to e to the negative x if x is greater or equal to 0, and 0 if x is less than 0. That means that student X arrives sometime after noon and is more likely to arrive promptly than late. So this probability density function, e to the negative x, becomes smaller as time passes. So the student is more likely to arrive promptly rather than late. And f2 of y is equal to 1 over 50 times y if 0 is less or equal to y less or equal to 10 and 0 otherwise. And that means that student y arrives by 12:10 and is more likely to arrive late than promptly. So this increases as y passes. After student y arrives, they will wait for up to half an hour for student X, but student X won't wait for student Y. And we're asked to find the probability that the two students meet. Because the events X and Y are independent, the joint density function, f of x comma y, for student X and Y's arrival time is the product of the individual density function. So we have that f of x comma y is equal to f1 of x times f2 of y. So that is equal to the double function 1 over 50 times e to the negative x times y. So we just multiply the two individual density functions. And this happens if x is greater or equal to 0 and 0 is less or equal to y less or equal to 10, and it's 0 in any other case, so 0 otherwise. Since the student X won't wait for y, they won't meet unless the student y arrives earlier, so we have that x capital should be greater or equal to y. And additionally, if the student Y will wait up to half an hour, but no longer, so they won't meet unless the difference between X and Y capital is less or equal to 30. Therefore, the probability that the two students meet will be given by P of the set of random variables X capital and Y capital belongs in the region D, which we'll sketch afterwards. And the region D is actually a parallelogram. So if we sketch that region D, we have X, Y, and we have X should be greater or equal to Y. So therefore, if this is the line X equals to Y, we only consider the region that lies on the right side of that line X equals to Y, since X should be greater or equal to Y. And now we also have that X capital minus Y capital is less or equal to 30. And that gives us another line that hits the x-axis at 30. So this is the line x minus y equals to 30. And we only consider the left side. So the left side of that line. And we can close that parallelogram since we are given that y has a maximum value of 10. Therefore, this is the region D over which we'll integrate. Therefore, D is the set of all points x capital, y capital, such that, and we consider that as a type 2 region because it will be easier to evaluate the integral. So we have that 0 is less or equal to y capital, less or equal to 10, and y is less or equal to x capital, less or equal to y capital plus 30. Therefore, the probability that the set of random variables x capital and y capital belong in the region D is equal to the double integral over the region D of f of x comma y times dx dy. So that is equal, if we substitute now, to the integral from 0 up to 10 for y capital and the integral for y up to y plus 30 for x. And we have the joint density function, which is equal to 1 over 50 e to the negative x times y times dx dy. So that is equal to, we pull out the 1 over 50, we have integral from 0 up to 10, and we have y, and we integrate e to the negative x dx will give us a negative e to the negative x. And we evaluate that between x equals to y and x equals to y plus 30 times dy. That is equal to 1 over 50 integral from 0 up to 10 of y. And we evaluate the negative e to the negative x. For x equals to y plus 30, we'll have a negative e to the negative y plus 30. And then minus the negative, which will give us a positive e to the negative y times dy. And that is equal to 1 over 50. We have integral from 0 up to 10 of y. And we have negative e. We now apply the identities of the powers. So we'll have negative e to the negative y times e to the negative 30 plus e to the negative y times dy. So that is equal to 1 over 50 integral from 0 to 10 of y. And we pull out a common factor of e to the negative y. So inside the parentheses, we'll have left 1 minus e to the negative 30 times dy. So that is equal. The 1 minus e to the negative 30 is a constant, so we can pull that also out. So we have 1 minus e to the negative 30 divided by 50. And we have to evaluate the integral from 0 times the integral from 0 up to 10 of y times e to the negative y times dy. Using the integration by parts here, we have y e to the negative y, 1, and negative e to the negative y. So that will give us 1 minus e to the negative 30 divided by 50. And then we'll have a negative y times e to the negative y evaluated between 0 and 10 minus the integral of negative e to the negative y dy from 0 up to 10. So that is equal to 1 minus e to the negative 30 divided by 50. And then if we evaluate also the integral, we have negative y times e to the negative y. And then we have minus e to the negative y from the negative integral of a negative e to the negative y. That will give us a negative e to the negative y. And we evaluate all that between y equals to 0 and y equals to 10. So that will give us 1 minus e to the negative 30 divided by 50. And we have, if we pull out a common factor, we have a negative e to the negative y. And then inside the parentheses, we'll have y plus 1 from y equals to 0 to y equals to 10. So that will give us 1 minus e to the negative 30 divided by 50. And for y equals to 10, we have negative e to the negative 10. And then we have 10 plus 11, so we have a plus 1. We have negative 11 times e to the negative 10. And then for y equals to 0, we'll have a negative the negative e to the 0, so we have plus e to the 0. So that gives us 1 minus e to the negative 30 divided by 50 times 1 minus 11 times e to the negative 10. And if we plug that in our calculator, this is approximately equal to 0.02. So that means that there is only about 2% chance that the students X capital and Y capital will meet.